Hey, so this is Joe, and this is the 6th video in the 14th chapter of Stewart's Calculus, and we're going to be talking about finding maximum and minimum values of multivariable functions. So, a critical point, that's a familiar term. We used that in single variable calculus to mean either a maximum value, a minimum value, or a cusp point, I guess. This means the same thing in multivariable calculus. A critical point could either be a maximum or a minimum value, but it could also be what we call a saddle point. And a saddle point, if you imagine what a saddle looks like, a saddle point is a minimum value in one direction and a maximum value in another direction. And the point looks like the middle of the seat of a saddle. And so we find these critical points at a point AB when the gradient of a function f, so it would be the critical point of a function f, when the gradient of that function at point AB is equal to 0, 0. And of course this can work with more than two independent variables, and so then more than 2 zeros would be necessary, because the gradient function would have more than two components, but it works with any number of independent variables. This truth holds. You just end up adding more points and more components like that. And so this is how we find out a critical point. However, as you remember in single variable calculus, you have the first derivative test, or sorry, I should say the second derivative test, to figure out when a function is a critical point is a maximum or a minimum. And we have a similar second derivative test in multivariable calculus. However, because there are more than just there's more than just one higher order derivative for any given function, because we have more than one variable, the second derivative test is a little bit more extensive and requires a little bit more calculus and algebra to figure out. So I'm going to go over to the next screen and show you that second derivative test. So this is our second derivative test. We say if we have the gradient of f at a and b equal to 0, 0, meaning that there's a critical point at point AB, then we let a function d, xy, equal this 2 by 2 Hessian. We call this matrix, this matrix that we're taking the determinant of, we call that the Hessian. And so we make that equal to the determinant of this Hessian higher order derivative matrix. And so that means that d at point AB is equal to the partial second derivative of f with respect to x at AB times the partial derivative of f with respect to y, and that's the second derivative, minus, and then based on Clairaut's law, these two second order partial derivatives, the mixed ones, are one and the same, so minus the square of that mixed higher order partial derivative at AB. And then we say, and then we figure out what d is equal to at that point, and if it's greater than 0, and if the second partial derivative of f with respect to x is greater than 0, we say that there's a minimum at point AB. And if d at that point is greater than 0, and the second partial derivative with respect to x at AB is less than 0, then we say that there's a maximum at point AB. And if d at AB is less than 0, then we say that there's a saddle point at AB. So that's our second derivative test. And those are really the two things you need to do in order to perform unconstrained optimization, or find maximum and minimum values for an entire function without constraints. So therefore, you'll mostly be dealing with local extrema at those points. This is all you need to know in order to get that done. So now let's move on to some practice problems, which we're going to do right here on the next screen. So we're going to do number 14 on page 978 in your book, and the question asks us to find the local extrema of the function f of xy is equal to y cosine x. So the first thing we need to do is find the critical points of this function. We do so by finding the gradient and setting it equal to 0. So we'll find the gradient of f xy, the gradient vector, and the partial derivative with respect to x is going to be negative y sine of x, and the partial derivative with respect to y is going to be cosine x, like that. And so now we need to set both components to 0, so we're going to get two little equations right here. We're going to get negative y sine x is equal to 0, and we're going to get cosine x is also equal to 0. So since this side only has one variable in it, we're going to start with that one. When is cosine 0? Well, it's 0 at pi over 2, and then you add pi to that infinitely, but we're just going to deal with pi over 2 for now. So pi over 2 is x, and then we can plug pi over 2 in for x right over here, and that's going to make this all 0. Oh, sorry, no, that's going to make this 1. So we have negative y is equal to 0, and then y is equal to 0. So we have, there's a critical point at pi over 2, 0. And now we need to perform our second derivative test to see what kind of critical point this is. So we're going to get our general formula for our little d equation, so d in terms of x, y, and that's going to be del squared f times del x squared, del squared f times del y squared, minus del squared f del x del y, or you could do the other way around as well, and all that squared. And that is going to be equal to negative y cosine x, and the second derivative with respect to y, well, that's just a constant for our intents and purposes, so that's going to be a 0 minus, and then we're going to get a negative sine x here, and you can try it with either component and you'll still get a negative sine x. You square that, so that's going to be a 0, or we should just say negative sine squared x. So now we're going to have to find our d at point pi over 2, 0, and that is going to be a negative 1 squared, because you plug in pi over 2 for sine and you get a 1, and so that is going to be negative 1, and that is less than 0, so therefore there's a saddle point at pi over 2, 0. And that is how we do a constrained optimization problem, and that's just about all there is to that. So now, so that's it for this video. Stay tuned for the next video. It's the last video in differential multivariable calculus. We're going to be talking about Lagrange multipliers. So stay tuned. Thanks.